Hi, I'm here to present our work on human-robot commensality, bite timing prediction for robot-assisted feeding in groups. In the United States, 27% of people have a disability, and almost 24 million people need help with activities of daily living. Feeding is an example of one of these activities of daily living. Being fed every bite of food is often challenging for a care recipient to accept socially, and eating independently with friends and family is one of the most memorable and important activities for people with mobility limitations. Feeding also happens to be very time consuming for caregivers. Generally, eating is a very social activity, but it's also a delicate dance of multimodal signals using gaze, gestures, facial expressions, and speech, just to name a few.
The act of eating together socially is known as commensality. Previous work with robot-assisted feeding systems mostly focused on human-robot dyads.
In this work, we aim to learn when a robot should feed someone in social settings. Robot feeding can be split up into 3 different steps. The first is bite acquisition, where the robot picks up the food item, as we see in the video over here. In the next stage, the robot has to figure out when to feed the person. We see the robot over here move to the rest position after it has picked up the food item, and needs to decide when to move towards the person to feed. In this work, we focus on this step in different social settings. And this step is challenging because in social scenarios, the robot should feed so that it doesn't interrupt the flow in conversation.
Then, once the robot decides to feed the user, it moves forward and the user tilts their head and takes a bite of food.
So, the question we want to answer is, how should an assistive feeding robot decide the right timing for when to feed the user in these ever-changing and dynamic social dining scenarios? To do this, we introduced a human-human commensality dataset, which contains groups of people eating. Commensality is the practice of eating together. So in our dataset, we have triadic groups of people eating while being recorded with a camera setup in the center. With this camera, we have individual RGBD views of each person. We have 30 triadic sessions with 90 people eating. Overall, we have 18 hours of video. This dataset is annotated with when people put their utensil inside the food, lift it off towards their mouth, and then takes a bite of the food, along with similar annotations for napkins and drinks. When a person lifts their fork off the plate to eat, we define this as their intention to take a bite of food, since within some time horizon, they will be taking a bite of this food. Given this definition of intention, we build a model which we call the triplet social nibbling network, or triplets on it. This is because the model uses features such as gaze, head pose, face and body key points, and speaking status from all 3 of the participants. We use the time since the last bite of food was taken and the number of bites of food eaten by the user, and we call this the user's bite features. And we use this as an additional feature that we tack on at the end because it provides some temporal information that we might not get from other features. Our dataset, however, has been on this human-human commensality data, but our goal is to feed in social scenarios on a robot, and we call this human-robot commensality. The features from someone self-feeding are inherently different from someone using a robot-assisted feeding system. For example, in body pose, a target user with mobility limitations would largely be still, which is different from the training data. We want to transfer bite timing predictions learned from human-human commensality cues to human-robot commensality scenarios, so we designed couplets on it, a variation of triplets on it. Here, we entirely ignore most of the features from the user, looking only at the user's bite features. More details on these models and baselines are in the paper. We find that triplets on it performs the best over other models such as an SVM and TCN, as we see in the middle rows over here, with higher accuracy and precision, as well as a higher normalized MCC score, which indicates it accurately predicts when the robot should and should not feed. Similarly, we find that couplets on it performs the best when we restrict the user's features. As expected, performance drops compared to the triplets on it model. In the human-robot commensality scenario, we add a robot to feed the user. To figure out what the preferences of the users are, we design a between groups user study with 3 different bite timing strategies, which each group is fed 10 times with these strategies. We test this on 10 triadic groups of people eating, where one of them is fed by a robot. Of the three conditions, the first one is our learned condition, which uses couplets on it. We use the last 6 seconds of features to sample couplets on it every 3 seconds to decide whether the robot should feed or not. We also add a fixed interval condition, where the robot waits 44.5 seconds. This number is a scaled average time from the human-human commensality data for how long the robot should take to feed a user after it has picked up a food item. The standard method to initiate feeding is a manual trigger, such as a user opening their mouth. In this condition, the robot asks,
"When ready, look at me and open your mouth."
And then once a user opens their mouth, as we see here, then the robot begins to feed the user. From our 5-point Likert scale questions in our post-trial surveys, we find that the mouth open strategy is generally distracting compared to the learned and fixed interval conditions. We believe this is because the mouth open strategy prompts a user using a voice interface, and that can disrupt the rhythm of this conversation. But when given a forced choice question on which conditions the users and codiners preferred, we find that the learned condition is largely more preferred. The problem of feeding people with mobility limitations in social settings is important. People with mobility limitations find eating independently with friends and family as one of the most important and memorable activities. So this work is a step towards socially aware robot-assisted feeding for people with mobility limitations. Thanks for listening.